It's a pleasure to be here again. I was back, we were checking Bud's calendar, it was September 25th that I was here, and I told you what ice sheets hate. Do you remember what ice sheets hate? Water. Very good. So I've had a good trip already, you remember. And the work I did in polar research really sort of naturally led to a lot of polar researchers being drawn into this much larger issue of climate change. And you'll see sort of how polar research becomes that gateway into global climate change. So whether we wanted to or not, we became part of that discussion, debate, battle, call it what you will. And if that's all I was going to talk about today, I really quite honestly think I'd waste my time and your time just preaching to the choir. So I'll talk about some of the science, yes I will, but I also see you as ambassadors of the message that the scientists are putting out to the public, trying to get the public to understand. And so what I want to do is to present the science in a way that increases your confidence in the validity of the science so that you have the confidence to engage others you know, and we all know others who are skeptical of that science or actually just flat out deny the science. If all we do is talk amongst ourselves in our echo chamber, we're really not going to make any progress. So hopefully by the end of this presentation, you'll have more confidence in your own position vis-a-vis climate change science being caused by human use of fossil fuels, and be so confident that you'll engage others. That's my objective in this talk. So I may go kind of fast through some of the science, but I think you probably already know a lot of that already. And hopefully I'll present it in a way that you'll find engaging and maybe open some new avenues of thought. So, apologies to any psychologists. I've abused the term bipolar disorder, but it was just too cute. I couldn't pass it up. And we do have two poles. And the people doing the live streaming, I like to wander around and wave my arms and all. And so I'm doing this with one hand tied behind my back because I have to hold the microphone, and to try to keep me at least within a circle that they can keep me on the screen, I think I'll just keep punching my computer to advance slides. So let me introduce you to the two poles, the Arctic and the Antarctic. You know, they're both cold, they're both bright, but actually there are some very interesting asymmetries between the two. The Arctic is actually an ocean in the central part where the North Pole is, and it's surrounded by continents. But in the Antarctic, you find just the opposite situation. The big ice sheet, 90% of all the ice on the planet, sits right there where the South Pole is, and it's surrounded by an ocean. And that has some interesting climatic consequences, the fact that the two poles are sort of configured, land and ocean, opposite from each other. The other interesting thing about the poles is that if you look at the three places on the planet that are warming faster than any other places, the top three, two of them are in the Arctic, and one is in the Antarctic. So the Canadian Arctic, the Siberian Arctic, and the Antarctic Peninsula are the top three places warming faster than any other place on the planet. And you may wonder why that is, but hopefully in 5 minutes you'll feel you know why. The other obvious thing about the polar regions is ice is in charge. Ice really rules everything. If you're in the polar regions, you have to consider ice. If you're just studying climate, if you're looking at the land, you're looking at the ocean, you have to worry about the ice. Even if you're looking at the soil, you have to worry about the ice in that soil. If you're some part of the ecosystem, you have to worry about the ice. When the ice is there, when it isn't, when the winters are long, when you have the long winters and when you have the short summers. So in the polar regions, it's all about the ice. But we like to say that what happens in the polar regions doesn't stay in the polar regions. So that polar ice and the changes in that polar ice really do affect the rest of the planet and therefore affect our lives. So even though we may sort of disappear to go off and do our research in the polar regions, what we're doing is actually relevant to the rest of the world. So the disorder, sort of everything going on in the polar regions is all sort of disrupted right now. If you study what I studied for my career, the ice sheets and glaciers there, well, I gave a whole presentation on that back in September about how they're changing in both hemispheres. The Antarctic ice sheet and the Greenland ice sheets are shrinking, they're going faster, they're thinning. A lot's going on those ice sheets that's affecting sea level. But you already heard all about that, so I'm not going to focus on that. But sea ice is the other big component of ice in the polar regions. This is the frozen ocean. This is unlike glaciers and ice sheets that are very thick ice sitting on land. This is the frozen ocean, only a few feet thick, but very extensive and very dynamic, moves around. And I will be talking about sea ice a bit more because it's a terribly critical part of the climate story. But also permafrost, the soils, they're thawing. And so that's an important change, especially for the people living in the Arctic regions right now. You know, roads are buckling, buildings are slumping, falling over. It really is disrupting their life as permafrost thaws. And you might think, well, that's their problem. But the other consequence, direct consequence of permafrost thawing is the release of a lot of methane, 20 times more powerful greenhouse gas than carbon dioxide. That methane release is a big deal that doesn't stay in the Arctic. And then snowmelt as well is arriving sooner. That isn't just in the polar regions. So I talked about that already. And I think last time I showed this kind of plot that over the course of a few years, maybe a little bit more than a decade, how the Greenland ice sheet is shrinking over time. It grows a little bit during the winter and it decreases a little bit more than that during the next summer. So it goes up and down. We see an annual cycle, but overall the Greenland ice sheet is shrinking, raising sea level. And that pattern is not uniform over the ice sheet. It is focused in those areas that are very dynamic where there are fast outlet glaciers. But those of you who were here in September, you remember all that. So let me keep going. If we look at Antarctica, the annual cycle isn't quite so clear there because it's 10 times larger than Greenland. You have a lot of different weather systems all at the same time operating in Antarctica, but the same basic story. It's shrinking over time and contributing to a rise in sea level. We know that story. Oh, but there was a recent paper, just came out last week by Eric Grignot and others that look at that rate of mass loss. And I thought that was an interesting statistic to put there, that right now it's losing mass about 6 times faster than it did 40 years ago. So we know that the loss of the big ice sheets is accelerating over time. And we know that's the link between what we see in these ice core records. This is from deep sea cores that we can measure from the types of coral in those cores, how high sea level has been in the past. This is 400,000 years, more than 400,000 years. And it goes up and down with the ice ages. Sea level goes up and down because the ice sheets grow and shrink. And the ice sheets grow and shrink because the climate's getting warmer. So we know these records are tightly coupled with each other. And that was part of, again, the September story that I told. This record is one of the most important climate records. The fact that we can do this, and having done that, it's so clear to us now that temperature and sea level are tightly linked. And the link is obviously ice sheets. No other system on the planet changes so much to be responsible for that. But let me move to sea ice now, because as I said, that's an important, equally important element of the polar regions that affects global climate. This is sea ice. These patches of frozen ocean. Sometimes they're very extensive, sometimes they're quite small. The wind and ocean currents move them around, they bang into each other, they sometimes pile up into pressure ridges that are maybe 10, 20, 30, maybe even 50 feet thick. But it's a far more dynamic system. And it's easy with satellites to measure how extensive that ice pack is in the Arctic. So you see how extensive the ice pack was at the end of the summer in 1979. We like to focus on the end of the summer to measure the extent of the sea ice, because once the air temperature drops and it starts to freeze more ocean water, then you've hit that minimum and you start to grow more and more sea ice. So we always like to measure that minimum right at the end of the summer. And we do that 1 year after the next, after the next. That composite there is what it looked like in 1979. And then this is just that record of how that's changed over time. So we started out between 6.5 million square kilometers, and it's been going down. There are interannual variations, but it's been going down. And that composite image in the background there right now is what it looked like at the end of the summer of 2012 when it hit this low point. But the point of showing this is that that purple or magenta box outlines the lowest 12 end of summer extents of sea ice, and they're all in the last 12 years. So we've gone from a state where we have, about between 5 to 7 million square kilometers to a state now where we have more like 3 to 4, 4.5. So it's been almost a complete shift in the state of the Arctic sea ice. Why is that important? It's because of this thing that scientists call the ice albedo feedback. Albedo is just a fancier name for reflectivity, if you will. And as I put in the asterisk here, this is the strongest feedback in the entire climate system, so it matters. And what I mean by feedback system is if you make a change, the consequence of that change is to drive even more of that change. So it's a self-reinforcing process. And I put some numbers up here. So we have the happy sun here shining on the Arctic. It's a good day in the Arctic. And the essence of the ice albedo feedback is the difference in reflectivity between bright ice and dark ocean. So if you have a patch in the Arctic where you have some sea ice and the sun is shining on it, about, what I say here, about 85% of that energy is reflected. About 15% is absorbed. Okay. Now what about the patch of ocean right next to it, dark ocean? The sun shining on that patch, most of that energy gets absorbed. In fact, about 93% of that energy gets absorbed. So only 7% reflects out. So if you have a patch that was sea ice and it's become ocean, all of a sudden now you're absorbing 6 times more of the sun's energy, 6 times more. And that's going to warm up that patch, and there's going to be more ice that melts and exposing more dark ocean. That's why it's a self-reinforcing process. And that factor of 6 is why it's such a big, major, the leading feedback system in the entire climate. So how much sea ice is in the Arctic really does matter. So that plot of it going from 6 to 7 million square kilometers down to 3 to 4 is a huge deal. I can back up that statement if we just look at this. This is an animation of every 5-year interval of the average temperature for different places across the globe. And you see that over time, the polar regions in particular warm up, and red colors are warmer, getting warmer over that time period. Maybe I'll even run that one more time. So it's in that Arctic where we have all this warming taking place. Remember the 1 and the 2, the Canadian Arctic, the Siberian Arctic warming up faster than any other place. This just says the same thing. Other places that are warming up are the land areas. There are some places in the oceans where over this time period it was slightly cooling. It has to do with deeper circulation of the ocean waters. But the basic message here is that in the North Polar region, we have more warming than any other place across the globe. And that time series started in 1950 and then continues to about 2014. So more than half a century we've been watching this happen. because of that ice feedback. I mentioned permafrost thawing, methane, very bad. So why the polar regions? Why we see all this happening in the polar regions? And actually the explanation is quite simple. When we think about polar regions, you got to think about ice. And with this ice albedo feedback, it's whether you have ice or whether you have water. Well, if you have ice that's just about ready to melt and you warm it up a little bit, big change happens. It goes from ice to water. Totally different material. I mean, molecularly it's the same, but it really is very different. It's not bright, it's dark, it's a solar radiation. It moves around a whole lot more and water moves around a whole lot more than ice does. So the contrast you get in the polar regions when you're taking some ice, just adding a little bit of heat, and you start to form water, that's a huge change. You go to the tropics where maybe it's 70 degrees, 80 degrees, and you warm it up half a degree, okay, it's 80.5 degrees. Big deal. You know, you haven't changed sort of the dynamic of the system. But in the polar regions, you have. That's why the polar regions are where we see all this dramatic change. Does that make sense to people? It's actually quite a simple explanation. But it's why why you, as a polar researcher, you couldn't avoid this climate change issue. That's the front lines of climate change. That's where we see the changes so dramatically. It has global consequences, but that's where the folks at NASA and NOAA and doing all their satellite observations and analyses, why we keep going back and seeing all these huge changes in the polar regions. It's because of this phase change. You're changing ice to water. And you don't do that anywhere else across the globe. So, I'm not sure if this slide's going to work, but we'll see. Okay, so you can pose the question, is human use of fossil fuels responsible for recent climate change? Now, if you poll the pundits out there, you can find half of them say, absolutely true. You can find half of them say, absolutely false, it's a hoax, these scientists are just feathering their funding nests, and you can't trust them. So there's absolutely no doubt, depending on which channel you tune to, right? So if you ask the public, actually the most recent poll is about 2 to 1. You have people, the majority of the American public at least, feel that the answer to that question is human use of fossil fuels responsible for climate change? They feel the answer is yes. So you have this fuzzy middle, and you certainly have those who feel it's not true. Let's ask scientists, climate scientists. This is sort of how climate scientists would poll on that question. But 97% say yes to that. And this maybe out here, those aren't really no's. Those are just those dyed-in-the-wool scientists that will not make any unequivocal statement. They have to have that plus minus a little bit. Well, there might be a caveat, there might be this, might be that. They just aren't willing to sign on to the unequivocal statement. They aren't saying no. They're just saying, well, I don't want to say yes. So another way of illustrating that, there's a room full of scientists there, and it's only these few who are just kind of scratching their heads that aren't sure. So, I mean, think about any other issue when this was the pro and con of that. Medical issue, real estate, buy a stock, whatever question you want to pose. If this was the result of the experts, I think you would, I don't think I'd find any disagreement here. But I love this statement. What's the use of having developed the science well enough to make predictions if in the end all we're willing to do is stand around and wait for them to come true? So it really does demand action, right? So you don't get off easy. There's stuff for you to do. And I applaud Transition Fidalgo and Friends. You're pretty active in this. Bud showed me all the presentations that have been hosted here. It's an impressive list. Here's my message. I like to really boil it down to an easy mantra that you can take back with you. It's CO2, it's us, it's dangerous, and it's now. So I want to sort of flesh out each of these points. We'll start with those two. Again, one of the most important climate records ever collected. And that's that same temperature record, although it goes back 800,000 years now, twice as long. And you see the ice ages and the interglacials in there. But the other one isn't sea level, it's CO2, which comes out of the same ice core. So we know the timing isn't in doubt. And so we know from lining up these two records and the fact that they co-vary, that one either can cause the other. Actually, it can go either way. You can warm up the Earth and you will produce more carbon dioxide. There is a feedback there. But more often than not, it's CO2 increasing first and temperature follows with warming. Okay, so greenhouse gas, and CO2 is the most, because it's far more abundant than some of the more powerful greenhouse gases, it has the greatest effect on this relationship between the Earth's temperature. And another way I want to illustrate this is with the first video that I'm going to show. And it starts with a piece of this. And what we're looking at here is CO2 measured in the atmosphere at Mauna Loa Observatory. And it goes up and down. It goes up and down annually because during the springtime, plants there's far more continental area in the northern hemisphere than in the southern hemisphere. So in the northern hemisphere, spring and summer, you have a lot of plants growing. That sucks up CO2, and this goes down. In the fall and winter, those plants die, releases that carbon back into the atmosphere, and this goes up. So you have this annual cycle. So the Earth breathes in and out CO2 on an annual basis. But you see that the trend is increasing. We'll talk about what that trend is. But what I want to show in this video is I'm going to work backwards in time. This is sort of about now. That's 1980. But we're going to go way back in time, just to help give you the context of sort of this pace of increasing CO2 and to show you what that really looks like on the longer time scale. So we'll see if this works here. Play this. Whoops. Try to enlarge it. Okay, so here you see this annual cycle. The blue one is South Pole Station, which is out of phase for an interesting reason that maybe I'll mention in passing with another slide. But focused on the red one, that's the one that David Keeling started during the International Geophysical Year at the Mauna Loa Observatory, and his son now continues that record. This probably also is one of the most important fundamental climate records ever collected by people on the planet. So now that's sort of the slide I just showed as the introduction. Now we're going to start pushing more and more data in from the left. And this time axis, we're going back a few more decades. This is when that record at Mauna Loa started. Then we have to go to other data sources. And now we're going back centuries. And this is sort of what the carbon dioxide level was before we started to burn wood and coal and oil and gas. Now we're putting tens of thousands of years into this, jamming this in. So you see how that record here is just getting squashed up along the right edge. And now you have your ice ages in there. Now we have 300,000, 400,000, 600, back to 800,000 years. So it puts all that record, I think, in a really powerful context of you can make any line look steep or shallow depending on how you choose your axes. But if you are careful and honest about your axes, you will get, I think, a better appreciation for the pace of change. That's sort of the final slide. And the fact that for most of this time period, the last million years, give or take, that CO2 has stayed within this envelope. We are so far outside of that envelope. I mean, that's why we say climatically we're in uncharted territory. Okay. Why do I say it's us? Well, there's some arrows with some numbers here, but let me walk through it. humans, we know how much human activity is, how much carbon dioxide is being produced from human activity, burning fossil fuels, because we buy it, we sell it. And so there's just no doubt about this number. And on an annual basis, it's about 29 gigatons of carbon per year. Nobody can appreciate how large a gigaton of carbon is, but it's a number that we're going to compare with some other numbers. Compared to natural systems, that's not a real big number. The problem is we're not doing anything to reabsorb any of that carbon. We're pulling that out of these deep reservoirs in the form of coal and oil and gas and releasing it into the atmosphere very quickly. That was sort of the point of that animation. So if we look at natural systems, it's actually producing a lot more carbon dioxide from the decay of plants and exhaling animals and farting cows and all that stuff. It's a much bigger number. But there are a whole host of natural systems that are reabsorbing that carbon dioxide. In fact, reabsorbing more than natural systems produce. And half of what humans produce. But unfortunately, it's only half of what humans are producing. So there is a net excess of about 12 gigatons of carbon per year, which is that other plot that kept going up. It was going up at about 12 gigatons of carbon per year. We've got this all figured out. We have the numbers. We closed the budget. It's very well understood. So sometimes you might hear the statement that, well, humans aren't producing that much carbon dioxide compared to natural systems. And that's true. But we're not absorbing any of that, and natural systems can't keep up with what we're adding, that extra margin that we're adding. That's the problem. And one solution is to either make that 29 a much smaller number, or increase that absorption from almost zero to something that at least reabsorbs some of that carbon dioxide. There are different pathways to solving this, but that in essence, in rough numbers, is the problem. Another animation. Let's look at where that carbon dioxide that we're producing is coming from. Hey, NASA has a satellite for that. It's called Orbiting Carbon Observatory. It can measure the carbon in the atmosphere, and it can trace the carbon that comes from burning fossil fuels and discriminate that from other carbon dioxide. So what I'm going to show is an animation that wipes the slate clean at the beginning of the year 2011. Okay? And so you'll see up there 2011-01-01. That's January 1st, 2011. And we're going to go through the whole year, but we'll just kind of zero everything out at the start of the year. Okay? Let's run that animation. And so you can see up here, February, March, April, and you start to see where the carbon dioxide comes from. It's no real big surprise, I think, where it's coming from. Initially, it comes from China, and then after a while, we can see the eastern US, Los Angeles shows up, Eastern Europe shows up. Weather systems moves that around some. You can see it start to diffuse out from the weather system. It stays mostly in the northern hemisphere for almost the entire year, but it does work its way down to the southern hemisphere. That's why the South Pole up squiggly line was out of phase with Mauna Loa. But this is where humans are injecting carbon dioxide into the atmosphere. I just thought it was really fascinating to see where that's coming from. That's the point of that animation. So again, we know, we have the observations, we know what's going on. Okay, let me get back to this thing. And this is just sort of every quarter year I just looked at because I wasn't sure if the animation would work. So by the time we get to December again, it gets cold in China, and you can really see that they turn on the coal-fired power plants. Global warming continues. I won't even take any more time with that. It's dangerous. It's now. Why do I say that? I like lists. Top 3, top 2. What's the most dangerous consequence of climate change? Well, when I was here again back in September, I talked about rising sea level, but that's only number 3 on my list. It's fairly gradual, it's happening slowly, and it's easier to adapt to. I was really pleased to see that on your agenda later this month, you're going to have a talk on ocean acidification. That's my number 2. Almost half of the world's population gets their food from the oceans. The oceans really matter. And if you're going to start fouling up the chemistry and disrupting the ecosystems in the ocean, there's going to be some serious consequences of that. And I'm sure that, is it Beverly? Is it? Brooke will talk all about that, so I won't say any more. Number 1 on my list is this one. This is where it hurts. This is where people are dying. This is really where the rubber meets the road. Number 1, without any question in my mind, is the fact that the consequence of this is more frequent extreme weather events. And we see this on the national news every night. I don't want to get ahead of myself. This is a slide that I used to show. It's actually from the insurance industry that tracked from 1950 on to, it's kind of out of date. It only goes up to the end of last century. The cost on a per year basis of extreme weather events, so the droughts, the snowstorms, the hurricanes, intense rainfall, all those kinds of intense weather patterns, and what the economic cost was, and what the insured portion of that was, which isn't a large number, it isn't a large percentage of it. And you see it going up, and you see my big green arrow on the far right, that now that we're in this century, it's even higher. So I did a really crappy job here, but what I took was information from another insurance company that allowed me to extend this, and I sort of fiddled with PowerPoint and stretched and shrunk and stretched things so that these two are on the same time scale and cost scale. So you see where we're headed. We see where we are. Highly volatile, a lot of interannual variability. Some years seem kind of quiet, but then there will be a year when there's all kinds of stuff going on, and you know what these years are, and you know what the events are, and the Hurricane Harvey and the Maria, and the whole litany of extreme weather events across the globe. It's real. Insurance companies live and die by being able to anticipate these and price them accordingly, price insurance accordingly. So it's now. It really is. Even during the Trump administration, this report came out from the U.S. Global Change Research Program. It came out in 2017, and it just included a litany of extreme weather events that are occurring right now. And I've underscored and bolded the importance or types of events, the daily tidal flooding. I was shown an apartment complex in Norfolk, Virginia, where people actually scheduled their errands with a tide table in their hand, so that they can get out to the cars and not have to wear their boots. There's an apartment complex that actually floods at every high tide. People continue to, and another anecdote. I think I showed it in the last talk. There's an island in Manila. I don't remember the name of the island, but a researcher was studying it. And he was surprised that when he was filming somewhere in the afternoon, the school let out, and there were kids playing basketball after school, normal activity. There was 6 inches of water on the basketball court. It happens every day. But they just continue to play basketball in 6 inches of water. And they refused the government's invitation to move the entire village because this is our home. We don't want to move. It's just stunning to see how this really impacts people's lives and how people are accommodating it. But get back on message here. Heavy rainfalls, heat waves, forest fires. We certainly know about that in this state. The earlier spring snowmelt. So the one statement I pulled out of this report was the human activities, especially emissions of greenhouse gases, are the dominant cause of the observed warming since the 20th century. There isn't any wishy-washy words there. Next year, volume 2 of this came out that was actually looking forward. The previous report was looking at what's happening right now. This volume 2 was looking at sort of what should we anticipate. And again, extreme weather events played a central role in this report. Drought and flooding will decrease corn and soybean yield, 25%. Ocean acidification comes up again, a biggie for this state. Infectious diseases. So it's not just sort of the sterile view of the climate that climate scientists have. You know, there's a real strong, powerful human dimension to all this that climate scientists should not ignore. Here, the one statement I pulled out: the global average temperature is much higher and is rising more rapidly than anything modern civilization has experienced, and this warming trend can only be explained by human activities. You know, we're not mincing our words any longer. It's about time. Oh yeah, do I even have, yeah, okay. Another paper came out that really shifted the paradigm for me. So I want to share it with you. And as backdrop, think of the Paris Agreement. You know, 140 countries, you know, signed on to it. Trump says he's going to pull us out of it. Does that matter? But you know, you think about the difficulty in coming up with these broad international agreements. I read this paper and I pull this figure out. What this paper did was say, okay, we have climate models, so we can say, okay, if we increase carbon dioxide a certain amount, what is the climate going to do? Okay, got that. Now I've got economic models. Okay, for a climate that does this, how is the economy of a given country going to respond to that? What's it going to do to their GDP? Is it going to go up? Is it going to go down? What sectors are going to benefit? Which ones are going to be disadvantaged? And they can put a cost, a societal cost of change to that. They can put a dollar number on it. And so they calculated this on a country-by-country basis. For every ton of carbon added to the atmosphere, what is the societal cost to the economy of each of these countries? And they plotted it. So what we have here on this scale is how much of the global emissions is any country responsible for. Okay, China is emitting more global carbon than any other country, 30%. The US is in here at 15%. That's sort of where you are on this plot, right or left. The size of the circle is how large your gross domestic product, your GDP, is. Okay, so we have some big circles. Those are the big, powerful economies. Now, where you are vertically on this axis is what share of, okay, there's a global cost in adding another ton of carbon to the atmosphere, an economic cost. And so there's a global total of that. Your share of that global total is where your country is placed vertically on this. So actually India is responsible for, of the global cost, societal cost, economic cost of increasing carbon, India is going to suffer a third of that, just that one country alone, because they're way up high on this. Saudi Arabia actually is fairly high, but a small economy, so it's smaller. And then the shade of the color is you divide by the number of people in that country. So India isn't quite as red as the US because there are a whole lot more people in India than there is in the US. So there's a whole bunch of information on this plot. But the way it struck me was that you don't need 140 countries to agree to any of this. If you take those big ones that are way out there, they're going to have the high social costs, they're risking the most by continuing to put carbon in the atmosphere. They're the ones that are going to lose the most. Russia, Canada, they're actually going to gain. So I'm surprised they're even part of the conversation, but we'll leave that aside for the moment. What you really have to do is get these big outliers. If they can agree, you've solved half the problem just by getting those three countries to agree on actions that they'll agree to and hold themselves to. So this, to me, completely changed the paradigm. I mean, if it were up to me, I wouldn't hold any more, international meetings. I would just say, okay, these few countries, let's sit down, let's close the door, let's solve this, because we can just ourselves. We don't have to get a whole bunch of other countries to agree to a lot of these actions. As long as we do, we have most of the problems solved right there. See? Powerful paper, really good. I do want to still spend some time here. Okay, why has it been so hard to communicate climate change? I've lived through this. Okay, I have 3 reasons. What a surprise. First thing is, people don't see, it's an invisible problem. By and large, people don't see greenhouse gases. Who remembers ever being in a car following a city bus that just spurred out this big, ugly, smelly, dirty cloud of diesel exhaust? I mean, if all cars did that, I'm not saying they should, but if they did, if we had, the proper vision to see CO2 being expelled out the exhaust pipes of cars, I think there'd be a greater appreciation for, hey, maybe that's not so good. We can't do anything about that one. Although we can. I mean, that animation that showed where CO2 is coming from, that kind of, removes that cloak of invisibility from that issue. The other one is can't feel climate. People feel weather. Nobody feels climate. Nobody sort of integrates their experience with the weather over 20 and 30 years. You just don't do that. So when scientists talk about climate, people think weather. And that actually is quite a problem that is starting to be addressed. I had an interesting conversation before the meeting started with someone, because scientists are getting the handle on trying to tie individual weather events to the climate predictions. And then finally this other one, and this is sort of a big catch-all, resistance to change and counter messaging. You can toss a lot into this, but there is a lot of momentum and inertia that you have to overcome, locked up in this third bullet. So let me talk a little bit about climate versus weather. And the best metaphor I can suggest is just think about a pair of dice. And you roll a pair of dice, and you don't know what the answer is going to be. You know it's going to be between 2 and 12, if they're normal dice. But you don't know what it's going to be. You roll that pair of dice 10 million times, and you can tell you with great certainty how many 12s you will have rolled, how many 7s you will have rolled. The statistics of that are really solid. So it is true, climate is more predictable than weather. So people that say, we can't predict the climate because we don't even know what the weather's going to be next week, just don't have it right. Climate has going for it statistical advantages. One way of thinking about greenhouse warming is we're loading the climate dice. We're not, and if you think about sort of the individual role of the dice as tomorrow's weather, we're loading those dice, and we're not going to get the same results. There'll still be familiar numbers. The weather is going to be familiar. It's not going to be like red skies or orange snow, but the frequency of the familiar weather will be changed. We're loading the climate dice. So weather is still going to be hard to predict and still going to be variable, but we can think about climate as changing the sort of the probabilities of what numbers we get, how many, how often we get certain numbers. So that I think is a useful way of thinking about climate versus weather. I'm going to go past these two. And we can show it in the data. So here, what I'm going to show are the compilations of, in the US, every day in the summer, for every weather station compared with what the average would be for that weather station on that day in the summer. And I'm gonna take 10-year chunks of this. So we're looking at a whole bunch of numbers. And we expect we'll see something like this. We'll see a distribution that there are places in the country that are a little bit warmer than on that particular day than they would have been on average. Some places that will be much warmer. Some places that will be much colder, but fewer of those way out there on the extremes. We expect this kind of distribution. We'll get to that later. So here are the data from 1950 to 1960. Tens of thousands of data in this. And we see, okay, statistics kind of holds true. 1960 to 1970, not changing too much. 70 to 80, still not changing too much. 80 to 90, start to get a sense of some changes. 90 to 2000, it's getting broader and it's shifting to the right. 2000 to 2010, and we had one more year. That's why we talk about a new normal. It's still this sort of pattern, this bell-shaped curve. We used to grade on that. I don't know what they grade on now. Do they even grade now? But it's a different distribution. It's more to the right. What that means is, on average, things will be a little bit warmer, but it's broader, which means there'll be more extreme weather. We'll still have cold days. We still have days like most of the country is experiencing. When I heard 75 or 80% of the U.S. is going to have temperatures below freezing. That fits. It's not going to be that common, but it will happen. So we see this in the data. Here's another metaphor. I'm just tossing out different ways that different sort of familiar arguments that you might find useful in your conversations that I know you're going to have now with those skeptics and deniers. Think about sort of a climate on steroids, if you will. A baseball player takes steroids. Their statistical performance will improve. It will change. They will hit more home runs. The problem is you can never point to a particular home run and say that was because they took steroids. So that's the same difficulty with trying to tie individual weather events and climate. Very, very similar. Okay, here's sort of the getting to the end here. Why should warmer climate cause more extreme weather events? I mean, ultimately, if you keep saying this, you're not going to be very convincing unless you can give a common sense answer as to why this would be the case. All climate models produce this result. Here's a really simple answer. Heat is energy. If we're going to warm the climate up, it's going to have more energy. And the way a climate system expresses itself is through weather. Climate is just the adding up of a whole bunch of weather. So if you're going to warm the climate, you have to have more extreme weather events. You have to have, because you have a more energetic system. You're stirring the pot. You're giving it steroids. It's really that simple. Think about Halloween. Okay, here we have our little climate models, running around with their paper bags and their costumes on. And they come back with a bag of candy. There's energy in that. It's sugar energy. It's not heat energy, but it's energy. And for those bad parents that let their kids eat half that bag of candy, they have extreme weather events happen in their house, guaranteed. It's a useful metaphor to explain why a warmer climate is a bad thing. It's not that half degree. Okay, that's going to change things in the polar regions. There will be consequences. But the really important ramification of that for the human element on this planet is more extreme weather events. We have tailored our lives to be fairly sensitive to those weather events. We live right next to the coast. Or the river, we are. Let me give a more scientific-y answer to that. Although that should suffice. But because we're experiencing this polar vortex, let me tell you how that fits into all this. If we think about the globe and the fact that, okay, it's spinning and the tropical areas warm up the air and it sinks in the polar regions, and so we have the atmosphere circulating around the globe, right? And it circulates in latitudinal bands. We have the easterlies that are in the tropics, the trade winds, and we have the westerlies. You know, our weather comes from the Pacific Ocean, doesn't come from Chicago. And the reason we have those bands is because of the temperature difference between the tropical air and the polar air, the cold polar air. So we have this zonal flow, and that temperature difference keeps that air circulating in sort of this band of latitudes. Okay, that's sort of the norm. Okay, so now we're going to look down on the North Pole, and we see that circulation. Okay. Well, color in that particular figure is elevation, and the reason I show that figure is that this nice circulation of air from west to east hits Greenland. Greenland is this big thing that gets in the way of the jet stream. It's that high that it interferes with the jet stream. The jet stream has to get over or around Greenland. It's really energy intensive to try to go over it, so it goes around it. That's where the wiggles in the jet stream come from. It's because of Greenland, because Greenland's this big ice sheet, high elevation, 10,000 feet in the middle of Greenland. That's where the wiggles in the jet stream come from. But now, remember that we had that shrinking sea ice, and the polar region, the North Polar region, the Arctic, is getting warmer than anywhere else on the planet. So that temperature difference that's driving this zonal flow that's trying to constrain the jet stream is getting weaker because that temperature difference is getting weaker. So the jet stream can wander latitudinally, farther north, farther south, a lot more often than it could before. That's the polar vortex. That's why half the country is experiencing freezing temperatures. Because that cold, you know, when they show you on the weather map, oh, here comes the Arctic air. It's going way down, you know, Midwest, it's past St. Louis, it's going to reach Natchez, Mississippi. It's because we're in this new normal, this orange state, where that jet stream can wander far more. In the Arctic, they're getting really warm weather out of that. It works both ways, but it disrupts the climate that we want to have. No, I live in Washington State, and I want the climate to be Washington State climate. I don't want California's climate, and I don't want Alaska's climate. I want Washington's climate. Well, this is stirring it all up. It's that new normal. It's that direct result of polar amplification, which is that darn sea ice, which is which is melting because of the warming, which is the whole climate system. Apologies if I go over, but I'm on a roll now. Okay. Change. Just that word. If I say change, how do you react? On a visceral human level, how do you react? You don't want to do that. No, I'm not going to change. You can't tell me to change. It's stressful for most of us, and we're going to meet it with resistance. You know, scientists, bless their hearts, I'm one of them, we message really poorly, and we don't always, my wife tells me all the time, I don't always choose the best words to communicate. Change was probably a really bad word. Global warming was probably a really bad term to use. Hey, but change can be good. You know, it's not always a bad word. It sometimes can be a good thing. If I could only show one slide for this whole talk, this is the slide that I would show. Okay, so you got me up there, you know, talking about climate change. So this guy stands up in the audience and says, what if it's all a big hoax and we create a better world for nothing? I mean, humor has enormous effectiveness in talking to people who have sort of a disinclination to hear you. So I love that. So it's probably change. You know, we can do better. We can maybe scrub that from our dictionary and put in improve, because that's really what we're talking about. We're really talking about improving the planet for ourselves. It's all selfish. I am so tired of hearing people say we can't respond to climate change because it's going to cost money and jobs. It's been said so many times that people think it's true. It's not true. It never was true. It will never be true. The cost, if we consider the cost in terms of dirtier air, dirtier water, the cost of not responding to climate change is so much greater than the cost of responding to it. Just in sort of human values. Sustainability is an economic winner for the common, for the majority of people. The only people that win in a scarce world are those people that control that scarce resource. They're the only ones. Everybody else loses. That is a zero-sum game. Sustainability should be our objective, as well as resiliency. I put that sort of in the financial security side, financial security column. Being resilient helps us avoid sort of the need for costly, what do I want to say, interjections or actions on a shorter time scale. You know, the more resilient we can be, the more financially secure we'll be as well. And so that's really sort of drawing to the close. The key points from this most recent report from the IPCC, I'm sure you're all aware of it. You know, they're just increasing the intensity of their messaging, you know, down there are various pathways to avoid this 1.5 degrees Celsius warming, or to avoid the 2 degrees Celsius warming. But there are various ways to do that. As I pointed out, we can just reduce our emissions, we can increase our absorptions. There are which countries we talk to, which countries we make agreements with. But you know, I was surprised. They put this 12-year timeline on this. But that's because the atmosphere already has enough carbon dioxide in it that once it equilibrates, we'll be almost to the 1.5 degrees Celsius there. So we really can't put much more into the bank there. We're just about at the limit. That's what they're saying. I'll go past that one. So it's time to close up and see if you have questions. So the polar regions really are a key piece of this. And the fact that ice sheets are shrinking and raising sea level is part of the fact that Greenland is so big and forces the jet stream to wander the way it does. The fact that sea ice has this ice albedo feedback, the strongest feedback in the entire climate system. It's warming the polar regions. It's helping to cause the jet stream to wander more north and south. That's all polar stuff that we're feeling the effects of, polar changes. The consequences are multiple and global. This is your mantra to take home with you. It's us, it's CO2, it's us, it's dangerous, and it's now. And my objective in this is to hopefully communicate this in a way that you feel even more confident in your position and your acceptance of the climate science, and can explain it in ways to those, dare to engage in conversations, those skeptics and deniers that I know you all know. I find those some of the most fruitful discussions, to find out why they feel the way they do. And if we don't do that, who will? And if it's not done, why would they ever support the position that supports the scientists in what we're trying to say? You have to help us in that. Thank you, and I'll stop there. So I think the deal here is that I have to give up this microphone. Is that right?
Yes. We're going to run it around.
Okay.
So
Oh yeah, that's right.
we are going to use, we're using 2 mics, one for the room and one for the online audience as well. So we're gonna have the opportunity to ask some questions of Dr. Bindschadler, and we're gonna start with questions in the room, and we'll do some alternating if there are questions online as well. So we've got a hand right here.
What are some ways that we could increase absorption of CO2?
Plant trees, compost, put less in landfills. I don't like geoengineering solutions. They leave me pretty, more than jittery, just flat out terrified. I don't think that's a good path. But so those would be, top of my list. Yeah, thanks for the question.
Okay, was there a question online?
We have an online question that says, what do you think will happen now that Brazil is run by a president who wishes to cut down the Amazon forest? One mistake scientists often make is that they allow their sort of political leanings to find their way into statements that they make, and it undermines our science. So when we respond to questions like that, it's very important to be clear what we're saying as a scientist who's involved in the activity, and what we might be saying just as a citizen that hears the news reports just like you do. I'm a firm believer in democracy and the public voice. So when I speak to people and they ask, hey, what should I do? I say there are two things you should do. One is sort of act locally, your own lifestyle. Your choices do matter. And the other is your opinions matter, and contact your elected representatives. In the case of the question that you asked, how do I react to that? Every time somebody with a lot of power expresses some stupid idea that's going to have all sorts of damaging climate consequences, it bothers me. They don't get it. They don't appreciate how important the issue is. If that's somebody that's in another country that has power, there isn't a whole lot that I can do as an individual. As a scientist, you hope that you can send them the IPCC report, but Brazil signed off on the IPCC report. So the fact that the current leader of Brazil doesn't want to accept that should sound pretty familiar to us in this country. And what I would do in this country is continue to contact your elected representatives at all levels of government and say how you feel about it. They do listen. They do listen. When I talked to, back in my days back in DC, and I was called onto the Hill more times than I enjoyed, and would have conversations with politicians, whether they be conservative or liberal. They wouldn't deny the science that I would present to them, but they would usually say after that, and until I hear that from my constituents, I have a lot of other things on my plate that they say they care about more. So that tells me that they do read their mail, and they do listen to their constituents. So keep that in mind, that they do listen, and it's not wasted time to contact your elected representatives and tell them how strongly you may feel about any issue, but tonight this is the issue. Yeah.
Is there another question here in the room? Burning questions. Is there another on here, back here?
Yes, I just wondered if the most recent IPCC report, does it, on that 12-year timeline, does it give any sea level rise projections if that goal is not achieved?
Yeah, I mean, the IPCC reports have always given sea level projections. I mean, they generally are produced every 5 years, I think.
Right.
This most recent one was a little bit different in its focus, but the IPCC certainly within its activity of trying to be the consensus document for globally produced climate science has always included projections of sea level. 12 years out, sea level isn't going to be a lot different than what it is now. The ballpark numbers I usually toss around is it will be a foot higher by the middle of this century and another 2 feet on top of that by the end of this century. And of course it varies regionally depending on whether you're tectonically going up or down at the shore. But for Washington State, it's not going to be that much different in 12 years. So it's not really about sea level. That's why, sea level isn't the #1 issue. If you read the report, the damage is going to be more frequent extreme weather events. That's the front line. That's where I think all of our attention really needs to be. That and ocean acidification.
Thank you for the talk and the science. You mentioned that you have 3 concerns, and also in your slide you're showing, I believe, India, the United States, and China as having the greatest effect. And one of my great concerns is going to be the migration of people on our planet due to the changing weather, drought, rains, and this kind of thing, especially in those large populations in India and in China. I think we'll be looking at the end of the century, considerable more movement on our planet than we even think we're going to experience now. Thank you.
Yeah, I would agree. I mean, climate refugees is going to be a growing problem. I think the climate science is done. We know enough. We've run enough simulations. We know more than enough to drive discussions and negotiations of actions of any wide variety of characteristics. The issues are going to be moral and ethical, I think, as a result of this. And so I expect, sort of as a physical climate scientist, it's going to be less about us and more about the more human issues. That's where we are right now. It's already happening, and yeah, very much so.
So when you showed that graph of I guess it was regarding going back 400,000 years, and then you said later that you could go back 800,000 years. Was that modeling, or was that from ice cores?
It's still ice. Yeah, going back, the 800,000 years is primarily an ice core record. Yeah,
I had no idea the ice was that old.
Yeah, the glaciologists have tried very hard to find the very oldest ice they can, exactly for that reason. So we can take these very dependable climate records as far back in time as we can. And the reason they're so dependable is that as the snow falls and the ice becomes denser, snow becomes denser and denser, it eventually forms ice. It traps samples of ancient atmospheres and locks it away for a scientist to happily come along and drill it out and then analyze it. So we found million-year-old ice. We've gone back even farther.
That's very good to know. I had some deniers online. I didn't know how to answer them, but that's good. Thank you.
Is there another question online? Nothing yet? Okay. Other questions here in the room?
This is not a question, has nothing to do with the presentation. I'm sorry, but I wonder, is there anyone in this room who can give me a ride home? I'm living on South Tidal.
Another climate refugee. climate talk refugee.
Okay, another question, Bud?
I think it becomes unfortunately helpful for some people if they're personally impacted, and I'm personally really concerned on the entire West Coast in fires. Do you share that worry?
Yes, yes. I mean, the Climate Impacts Group at the University of Washington, I would say, is all over this issue. You know, they have taken the IPCC reports, those climate model simulations and results, and brought it down to the scale of Washington State to be able to describe what the local impacts will be. And they are threefold. One is ocean acidification and the impact on the shellfish industry in particular, because the change of the chemistry of the ocean affects shellfish more than it does, I don't even know the right term for fish that swim. I guess all fish swim, don't they? The other is storms that drainage, catchment areas that get are primarily snow-fed more than rain-fed will be shifting over to being more rain-fed than snow-fed. So we'll still have, and we'll have more intense storms in the winter, but they'll be primarily more rain than snow. And the third is wildfires. And the fact that many species of trees will find it less beneficial to be in Washington State. So there will be some shift in the mixture of what types of trees you have in which forests. That's going to change. And those that aren't being, that are finding themselves disadvantaged will probably be adding more fuel for increased wildfires. I mean, that's what we're going to see here in Washington State, principally those three things: more rain than snow, and which has, you know, ecological effects, ocean acidification and the wildfires. Yeah.
I think we have time for one more quick question, if there's anything left. Okay. Well, I want to thank Dr. Bindschadler immensely for his very informative and for me, it was very interesting and exciting talk for us, and really challenging us as a community to take this on and do something about it. So I guess that would be my last question for you. Since you like lists, what are the top 3 things that Transition Fidalgo and this community can work on in terms of addressing these kinds of issues?
Wow, I thought I was going to get away with it. Number one would be do what I hope you're inspired to do after this, is have those discussions with people who may have honest concerns and skeptical views about some of what they hear. You will be a trusted source for them. They trust you more than they would trust me because they know you. So that would be the first thing. And if Transition Fidalgo and Friends can somehow facilitate that kind of increased discussion, all for the good. I think you would feel good about it too, and that will have some impact. And then I would say maybe facilitate individual members to do some more contacting of your elected representatives. Invite them to some of your meetings, perhaps. Host a town hall, you know, something like that. I think you obviously have some impact in your community, so leverage that to reach out to more people and not just people, you know, the preacher and the choir. You know, that's reach out.
Thank you very much. So, give him a big round of applause.
Well, thank you.